Now, covalent catalysis is a type of catalysis in which a transient covalent bond between an enzyme and substrate is formed. So there are changes to the reaction pathway. In an uncatalyzed reaction, A and B are bound to one another, and with the help of water, that bond is broken, and your products are A plus B. Okay, in a catalyzed reaction, X is going to exist as your catalyst, and in this case would be a biological catalyst. We have our same starter molecule, A, B, which are bound to one another. Then we have our biological catalyst, X, and what's going to happen here is A is going to become bound to X, and B is going to be released, and then with the help of water, we're going to form A independent, X independent, and B is independent. It's important that you look at your X as being the same as when you started the reaction. So what's important about this is that we're going to require a nucleophile on the enzyme. Now, amino acid residues that serve as very good nucleophiles are serines. You could have a thiolate, an amine, or a carboxylate. Okay, so if you had a serine, think about what that R group looks like. CH2OH. Carboxylate, well, you've got aspartic acid or glutamic acid. So CH2 here, okay. So that, yeah, you have to have a nucleophile in order for that reaction to take place. Now, metal ion catalysis, well, lo and behold, it requires a metal ion bound to the enzyme. This is going to interact with the substrate to facilitate binding and stabilize any sort of negative charges. This is largely, these are going to be participating in oxidation reactions, but they also could participate in reduction reactions. Now, after you understand enzyme mechanisms and how they're going to move along, which there are later videos that display specific mechanisms, it's important to know about enzyme kinetics. Kinetics is the study of the rate at which a compound interacts. So the rate of enzymatic reaction is going to be impacted by the enzyme, the substrate, the effectors, and the temperature. Two people who are very important for the discussion of enzyme kinetics are Leonor Michaelis and Menten. They made huge contributions to the field of enzyme kinetics, and basically the lens through which we look at enzymes and study enzymes is the lens that they helped craft. Now, why should you actually study enzyme kinetics? One, it gives you a quantitative description of a biological catalysis. You're able to determine the order of binding of substrates. You can elucidate acid-base catalysis. You can understand a catalytic mechanism. You can find an effective inhibitor, and you can understand regulation of activity. And if you wanted to, like, these are all specific reasons, or maybe not super specific, but these are all kind of good ideas as to why you'd want to study it. But whenever I see the word inhibitor, and I think about enzymes, my mind immediately goes to, well, drug development. And so that takes me to, whenever I'm thinking of drug development, I'm thinking about human health. I suppose you could cross out humans and just say health in general. But a good reason to study enzyme kinetics is to understand how the enzymes in your body process different materials, process metabolites, how you get energy or use energy, and that will give you good insight into how well yeah, I guess how you live and thrive and survive and everything like that. So, derivation of enzyme kinetics equations. You have to start with a model mechanism, identify the constraints and assumptions, and do the algebra. Now, our simplest model mechanism is E plus S yields reversibly our ES complex, and that ES complex goes in the direction towards our enzyme plus our product. One reactant, one product, no inhibitors. Now, the constraints and the assumptions. Our total enzyme concentration is constant. The mass balance equation for our enzymes is E tot. So our total amount of our enzyme is the free enzyme as well as the enzyme substrate complex. It's also implicitly assumed that S tot, so your substrate total, S plus ES, is comparable to the free enzyme concentration. So the amount, effectively, that means that the amount of the amount of substrate that is bound within the enzyme substrate complex is almost a negligible amount, because your S tot is effectively equal to S plus ES. Okay, so our steady state assumption is that a change in our ES complex concentration and the rate of formation of the ES complex formation is minus our rate of breakdown of ES is 0. Okay, so the formation of ES and the breakdown of ES, the difference between those is going to be 0. Now, what is the observed rate, or our V net, or velocity of our reaction? That is equal to our product formation over time. So dP over dt is our product formation over time. So the rate of product formation is the rate of ES breakdown to our product. Okay. So all of that comes into this the Michaelis-Menten equation. Again, Leonora Michaelis and Maud Menten gave us effectively this equation right here. Vmax, so the maximum velocity that your reaction is going to be catalyzed, times your substrate concentration divided by your Km plus your substrate concentration. Now, that is equal to Kcat times our total enzyme, or total free enzyme, our total enzyme concentration times our substrate divided by Km plus our substrate. So the first term that's presented there is Kcat, our turnover number. That tells you how many substrate molecules one enzyme molecule can convert to a product per second. Our Michaelis constant, Km, is an approximate measure of a substrate's affinity for an enzyme. So basically it's kind of a binding measure, or it's a number that explores that. And this is analogous to, similar to P50 of oxygen binding proteins. And so what that means is low Km equals high affinity. And vice versa, high Km is low affinity. So during steady state, the Vmax occurs when all of the enzyme is in the ES complex. It is dependent on the breakdown of that complex. So our rate times our ES complex concentration. The microscopic meaning of Km and Kcat depends on the details of that mechanism. These are two terms, however, that are very important for you to understand. Turnover number and our Michaelis constant. We're going to be exploring these a little bit more in a little while, but I hope this was helpful. I'll see you in the next video.